So next up, the Sun-Earth and the Sun-Earth relationships. The solar constant, GSC, is the energy from the Sun per unit time, received on a unit area of surface perpendicular to the direction of propagation of the radiation at mean Earth-Sun distance outside of the atmosphere. And as you can see at the image there in the right, you can base the statement right there. We have angles and such and diameters. So Earth's elliptic orbit. The elliptical path causes only small variations in the amount of solar radiation reaching the Earth. And you can base it again on the photo there. So next up we have the Earth's axis is tilted 23.5 degrees from being perpendicular to the plane of the ecliptic. So the axis of rotation remains pointing in the same direction as it revolves around the Sun, as you can also see there in the image, pointing toward the star Polaris. The constant tilt and parallelism causes changes in the angle that a beam of light makes with respect to a point on the Earth during the year, called the sun angle. So right there in the image, that is the sun angle. So the most intense incoming solar radiation occurs where the sun's rays strike the Earth at the highest angle. As the sun angle decreases, the beam of light is spread over the larger area and decreases in the high sun angles. During the winter, the Earth is oriented away from the sun, creating low sun angles. So that explains winter temperatures and summer temperatures because of the Earth's angle. So sun angle determines the intensity of energy. So next up, we have here air mass. The path length of solar radiation through the Earth's atmosphere in units of air mass, AM, increases with the angle from the zenith. So the zenith is over there. You can base it also in the picture right there. So the AM 1.5 spectrum is the preferred standard spectrum for solar efficiency measurements. The easiest way to estimate the air mass in practice is to measure the length of the shadows cast by vertical structure of height using the formula given in the middle right there. So air mass, or the AM, the ratio of the mass of atmosphere through which beam radiation passes to the mass it would pass through if the sun were at zenith directly overhead. Zenith meaning directly overhead at sea level. AM equals to 1 at sea. That's at sea level. AM equals to 1 when the sun is at zenith. AM equals to 2 for a zenith angle theta z of 60 degrees. For 0 less than theta z, or for 0 less than theta z and less than 70 degrees AM equals to 1 over cos theta z, as shown there in the statement below air mass AM. So next up we have here irradiance and irradiation. So what is irradiance? Irradiance is given with W over M2 and is represented by the symbol G. So it's like gravity, but no, gravity is small g. The rate at which radiant energy is incident on a surface per unit of area of surface. So irradiation now is given by J over M2 and is the incident energy per unit area on a surface determined by integration or irradiance over a specified time, usually an hour or a day. So next up we have insolation, is a term used to solar energy irradiation. We have then radiosity. Radiosity is the rate which radiant energy leaves a surface per unit area by combined emission, reflection, and transmission. So that is irradiance and irradiation. Next up, we have solar irradiance. So we have radiation and irradiance kanina. Now we have solar irradiance. In the design of photovoltaic systems, the radiation over one day is particular significance. Solar irradiance integrated over a period of time is called solar irradiance, which is the total power from radiant source falling on a unit area. The average daily solar radiation on the ground, GAV, or it's the average both over the location and the time of the year, can be obtained using the following relationship. So we have here the relationship below, or an equation right there. So where the average irradiance outside the atmosphere is 342 what's over m2. So solar radiation observed on the Earth's surface is 30% lower on account of scattering and reflection of radiation. And next we have here beam radiation. So the direction of beam radiation. The geometric relationships between a plane of any particular orientation relative to the Earth at any time and incoming beam solar radiation can be described in terms of several angles, latitude, declination. We have here Greek signs, also Greek letters also to represent it. Slope, surface azimuth, angle, our angle of incidence, zenith angle, solar attitude angle, and solar azimuth angle. And also we can base we have here an image where we can base our statement from. So we have here right there the zenith angle, slope, surface, and etc. So just base it with the Greek letters also. Next up, so still beam radiation. So there is a set of useful relationships among these angles. So equations relating the angle of incidence of beam radiation on a surface theta to the other angles are as follows, given in the image right there. Image of, it's like an equation looking thing. We have sine and cos right there. So next up,